Okay, YouTube, this is my first video in a series that I'm doing on trigonometric identities, and what I want to talk about in this video is kind of what we use trig identities for, what they are, and what we use them for. So let's go ahead and start with kind of what they are. What I've got here is just kind of a diagram here of our unit circle, and what I want to do is point out here that it seems that we have some angle in standard position. We're going to refer to this angle theta. You can tell that this is in standard position because its initial ray starts on the positive x-axis. But basically, this initial, this not initial side, but this terminal side crosses our unit circle at some point xy here, given this angle theta. And so what we know about this is this point xy, at least on the outside of the unit circle, the x value does indeed provide us with the cosine value, and the sine value is indeed provided by the y value. And so it is very fair to say that if we were to drop an altitude here for this given angle theta, we have this relationship of this right triangle here that's constructed thusly, where we have this is the length x, this is the length y, and then we know that because we're on the unit circle, we're of a radius of 1. I'm going to say that this is r, and r is specifically equal to 1. It'd be pretty easy to state the fact then that x squared plus y squared equals r squared. In this particular instance, certainly we get x squared plus y squared equals 1 squared. And so 1 squared being 1, we say that this is very true. The substitution I'd like to make, though, is simply this. We would say because on the unit circle the x values are the cosine of the angle, and because the y values are the sine of the angle, then what we're going to notice is really we could make this substitution here where we say this would be cosine theta squared instead of x squared. We could have sine of theta squared instead of y squared, and this would be equal to 1. And another way of writing cosine squared and sine squared would be as you see them over here. And so what you see, first of all, this cosine squared plus sine squared is an example of what we refer to as an identity. And with respect to an identity, okay, an identity is a statement that is true no matter what you put in for the independent variable value, in this case theta. So no matter what angle we plug in for theta, it is always true that the cosine squared of that angle plus the sine squared of that angle equals 1. The other thing that I want to make sure that we mention here is this. When we say cosine squared, like this right here, cosine squared of an angle, it really means the same thing as the cosine of that angle squared. And likewise, we write sine squared of an angle, we write it this way, and it really means the same thing as the sine of that angle squared. And the reason why we put it between the trig function and the angle itself is because if you were to write something like sine squared like this, you might make the mistake of thinking that we mean to square the angle. And so we always write our squared or cubed or fourth power, whatever the power is on our trig functions, between the angle and the trig function itself. But what we have here is an example of an identity that is true no matter what we substitute in for the angle here. And so with respect to an identity, okay, we have a whole list of them. And you can see that I've provided a screenshot of some fundamental trig identities. And we're basically going to focus on really these first three in this video here, and then moving onward we'll look at some of these other identities. But basically what we use these trig identities to do are really to evaluate trig functions, also to simplify expressions, and also to verify trig identities, okay? So with respect to evaluation, basically let's go ahead and start by taking a look at our reciprocal identities. These identities here, for instance, say that the cosec of an angle is really equal to 1 over the sine of that very same angle. So when we look at this reciprocal identity, essentially what it's saying is, for instance here, if we wanted to find, say, the cosecant of a 45-degree angle, we certainly know that this is the same thing as 1 over the sine of that very same angle there. And anybody who knows their sine of 45 knows that the sine of 45 is root 2 over 2. And in this particular instance, of course, since we're dividing by a fraction, we would have to multiply by the reciprocal, which comes out to be 2 over root 2. And anything times 1 is itself, so we get 2 over root 2, or 2 root 2 over just the 2. And so what happens is these 2's cancel out, we just get root 2. Okay. Long story short, what this is meant to say is essentially that, hey, the cosecant of 45 degrees, this thing right here, is really just the reciprocal of the sine of 45 degrees. So with our reciprocal identities, what we're going to see is that any of the reciprocal functions, say cosecant of an angle, secant of an angle, and cotangent of an angle, are the reciprocals of the sine of that angle, cosine of that angle, and tangent of that angle, respectively. And so what that means is essentially, if we have any trig function, we can always find the reciprocal value just by flipping it over. So that's kind of neat. If you know one trig function value, we can evaluate for its reciprocal just by reciprocating it. So if you know one trig function value, you really know two. Moving on to our tangent and cotangent identities. This is kind of a key identity right here, but what I want to point out is, at least with the unit circle up here, we say that the cosine value is x and that the sine value is y, but in terms of finding, say, a tangent value, remember that the tangent value really is our y value over our x value here. We say opposite over adjacent, or on the unit circle, y over x. But looking at the unit circle, we already know that since y represents the sine value and x represents the cosine value, you can see that we could really build this new relationship that says, well, then if you want to find the tangent of any angle, really what you're doing is you're taking the sine value divided by the cosine. And likewise, because cotangent is its reciprocal, we could say that cotangent really is cosine over sine. So with respect to these two identities that you see here, I'm going to write a little note here. Basically, if we know sine and cosine, we can find tan and cotan. As long as we know those sine and cosine values, we can always say sine over cosine is our tangent value, and also that cosine over sine, its reciprocal, is just the reciprocal tangent function, which is our cotangent function. So first things first, we set our reciprocal identities. Say if you know one trig value, you really know two because you can reciprocate it. The second identities here, tangent is sine over cosine, cotangent is cosine over sine. Those say that if you know sine and cosine, you can find tangent. And let's imagine if we knew sine, cosine, and tangent, the idea would be we could flip all of those over using the reciprocal identities, and we would have all 6 trig functions of an angle. So to finish up, we're going to look at our Pythagorean identities. And these Pythagorean identities here, these ones that you see, starting with the first one, is that we have sine squared plus cosine squared equaling 1. And the reason why this is called Pythagorean is because really we use the Pythagorean identity the same way that we use this. And so what this essentially means, I suppose, is that if we knew the sine, imagine that you know the sine of an angle. Then we would know its cosecant just because it's reciprocal. But basically, if you know the sine, what we could do is we could plug it in for this value right here, and then the only thing left we wouldn't know is cosine. So long story short, this Pythagorean identity allows us to, if we know sine, go find cosine. And if we know cosine, go to find sine. So the implications here would be, let's say for instance, I know that the sine of an angle is a half. Automatically, I would know that the cosine of this angle is also 2 over 1. But at the same time, because of our Pythagorean identity here, it says that if you know sine, you can go find cosine. What we could do is we could take this sine squared theta plus cosine squared theta equaling 1, and we could take out the sine value all together there, take out the sine function, and say, well, sine squared, since sine is equal to 1/2, then really this is just 1/2 squared. And so simplifying this and solving for cosine now, you could see that, checking this out, we have 1/4 plus cosine squared of theta equals 1. If we subtract a fourth from both sides here, if we subtract a fourth, that'd be minus a fourth, minus a fourth. Our common denominator on the right there would be 4/4, or sorry, 4, but we would have 4/4 minus 1/4, which gives us 3/4. And then the very last thing we want to do here is remove the square root. And remember that when you take the square root of a fraction, essentially we're taking the square root of the top over the square root of the bottom, which gives us in this case plus or minus 3, square root of 3, over just 2. And we could say that this is our cosine value right here. So the interesting thing about this is we started with sine, and we were able to determine cosecant just by using our reciprocal identities. And then also using our Pythagorean identities, it says if you know sine, you can go find cosine. We were able to discover what cosine equals. So if cosine is root 3 over 2, then now all of a sudden we know that secant is plus or minus 2 over root 3, or 2 root 3 over 3. I'm just going to put a box around that. But now also that we know the cosine and the sine, we could go find the tangent. We could say that the tangent, being the sine over the cosine, we know that our sine value here is 1/2, and that our cosine value is plus or minus root 3 over 2. Okay, and if we do this, we would have to multiply by the reciprocal, so we get 1/2 times 2 over root 3. I'm going to put the plus or minus there. We're multiplying though. So when we multiply, we get our 2's to kick out, and what we get in the end is 1 over root 3, or root 3 over 3, and I'm just going to station that plus or minus out in front there, so we say plus or minus. So now we would have our tangent value, and flipping this over, we would have our then cotangent. So the idea is that if we know our reciprocal identities, then we could always just be given the value of one trig function and go and find the values of the other 5 by using these identities here. Okay. So with respect to Pythagorean identities, what we basically want to say here is that if we know sine, we can go find cosine. If now looking at these other two, we have two other Pythagorean identities. 1 plus tangent squared is secant squared. If we knew the tangent value, we could go find the secant value by substituting, or vice versa. If you know secant, go find tangent. And also over here, 1 plus cotangent squared is cosecant squared is another Pythagorean identity. Basically, if we know cosecant, let's substitute it in and go solve for cotangent. Or if you know cotangent, go substitute it in and go solve for cosecant squared or cosecant. So what we're going to do really is put these to use in order to do exactly that. And so I've got a couple of examples I want to work through here, starting with this first one here. Essentially, what we're being told is that the sine of some angle is negative 5/13, and also that this is very true. We say that the angle theta is between pi and 3 pi halves. What we want to do, though, is use the fact that we know sine to go find the other 5 trig functions of theta. So to start with this, number one, what we're going to do is this. We're going to sketch the quadrant, or sorry, identify, let's just do this, identify the quadrant by sketching. So sketch the angle termination spot or quadrant. So essentially, the idea here is this. They've said that our angle is somewhere between pi and 3 pi halves. So essentially what we're being told is that this angle in standard position is somewhere between pi radians and 3 pi halves radians. And it certainly doesn't matter to me where I sketch it in. All I know is that my angle must be this angle right here, okay, this theta. So what we want to go do now is find the values of the other 5 trig functions using our Pythagorean identities, or sorry, Pythagorean, but our identities here, our fundamental identities. So let's start with this. If I've been told that the sine of an angle is negative 5/13, essentially the very first thing we should do is use our reciprocal identities to say that if I know the sine, then I know the cosine, or cosecant, excuse me, is its reciprocal. So I'm going to put a box around these two and say, look at that. Just by knowing our reciprocal identities, now I know 2 trig function values. So with respect to finding anything else here, now I could go find tangent, but the idea would be I'd have to know both the sine and the cosine. And right now, I only know the sine value and I only know the cosecant value. So here's what we're going to do. Looking at the Pythagorean identities, we're just going to pick one. And I noticed that because I know cosecant, I could use this one right here to go find the cotangent value. Or because I know the sine value, I could use this Pythagorean identity to go find the cosine value. I got to tell you, I'm very, very partial to using this very first Pythagorean identity, which is sine squared plus cosine squared is 1. So what we're going to do is this. We're going to say because I know that sine is negative 5/13, then it's very true. I'll write this over here. We say sine squared plus cosine squared is equal to 1. So the sine value, all we're going to do is we're just going to pop that out here. We're going to say because I know what it is, we can fill it in with what it equals, and it equals negative 5/13. So now all it becomes a matter of is just solving for what the heck cosine equals. So squaring our negative 5/13, I get 25 over 169 plus the cosine squared of our angle is equal to 1. Now I'm going to scroll over a little bit here. Because this is true, then we need to solve for cosine since that's what we're after. Now, notice that when we do these Pythagorean identities, on all of them there's a 1 involved. And the beautiful thing about a 1 is when you are trying to take something like negative 25 169 and subtract it from both sides, the thing here is that the common denominator between 1 and any fraction is going to be just the denominator of that fraction. So what we end up with here is this. I'm going to kind of drag it up over here. We have cosine squared of theta is on the left-hand side. On the right side, we have 1 minus 25 69. I'll even write that down. 1 minus 25 169, which means that our cosine squared is really 169 169 minus 25 169. And so what this yields is, I'm going to do a little mental math here. We basically get then that the cosine squared of our angle is equal to 144 on top, and this is 169. So to solve now for just the cosine of theta, recall that to undo a squared, what we'll do is we'll just take the square root of both sides. And the beautiful thing about this is that we know the square root of 144 and the square root of 169 should be 12 and 13, and very importantly here, we want to put a plus or minus out in front. So I'm going to tell you something here. I'm going to share something with you. The fact that we were told that this angle, it terminated in the third quadrant. We know that all trig functions are positive in the first, only sine is positive in the second, only tangent positive in the third, and only cosine positive in the fourth. So we were told that this angle terminates in the third quadrant, and that is important because when we look at our cosine value, we got a plus or minus when we solve for it, but we have to choose one. And because I know now that my angle terminates in the third quadrant, that means that the only thing positive down here is tangent, which means for the plus and minus here, it just must be just a minus because since we're in the third quadrant, our cosine value has to be negative. So we get negative 12/13. I'm going to put a box around this. So splendid. Now we know the cosine value. We can use our reciprocal identities to find the secant value, which is negative 13/12. Cool. So now, to find tangent and cotangent, the wonderful thing about tangent is that we always know that the tangent of an angle is equal to the sine value over the cosine value. So I'm going to write this out here. We say, now that I know my sine and my sine is negative 5/13, and my cosine is negative 12/13, we're going to need to multiply by the reciprocal here. So negative 5/13 times negative, and this will be 13 over 12. We get the 13s to kick out. We get a negative 1 here and a positive 1 here. But a negative 5 times a negative 1 is a positive 5, and a 1 times a 12, of course, is a 12. What this means is that our tangent value must be 5/2. And therefore, because tangent is 5/12, then we get a cotangent value of 12/5. So in terms of evaluating trig functions, you can see how these top three sets of identities here, our reciprocal, our tangent and cotangent, and our Pythagorean, come in really handy. And so what I'd like to try again here is, could we find the values of all 5 trig functions given this specific information that we have here? So I would encourage you to pause the video right now and give this a shot on your own. If you're interested in seeing what I end up with here, you can go ahead and continue watching. So let's just go ahead and start talking about where our angle lies in the first place. We know that sine is 4/5. We were told this. And we know that our angle is somewhere between, and I suppose if you want to do this in degrees, we say 90 and 180 degrees. So what this means is, with respect to our sketch, our angle starts here and terminates somewhere in the second quadrant, somewhere between pi halves and pi radians, right there. So we say here is our theta. So what we're going to do is we're going to say, well, starting with the fact then that sine of theta is equal to a positive 4/5, and that makes reasonable sense because sine must be positive in the second quadrant. Then we would know our cosecant value has to be 5/4. Okay, so we have sine and cosecant. Let's use our sine along with our Pythagorean identity here. Go plug it in for sine and go find cosine. So we have this. We have sine squared, so 4/5 squared, our sine value squared, plus our cosine squared value. It's equal to 1. When we square out our 4/5, we get 16/25 plus the cosine squared is equal to 1. When we subtract 16/25, we get cosine squared is equal to 25/25, which is this 1 here, minus 16/25, which ends up giving us a 9/25. So if cosine squared equals 9/25, then just cosine, after we take the square root of both sides, is going to be the square root of 9 over the square root of 25, which is plus or minus 3/5. So now, again, what we're going to do is we're going to assess the situation and say, depending upon which quadrant this terminates in, should our cosine be positive or negative? And because, again, it terminates in the second quadrant, then the only thing positive in the second quadrant would be a sine and its reciprocal. So we know that this cosine value, I'm going to write this again here, we say cosine, it must be a negative 3/5. So while we're at it, let's go ahead and determine our secant value. Because of our reciprocal identities, we know our secant value is negative 5/3. Okay. So now onward to tangent. Recall that tangent is y over x, or sine over cosine. So using our sine and cosine values here, we have 4/5 positive, which is our sine value, and negative 3/5, which is our cosine value. And we'll just rewrite this as multiplying by the reciprocal. So positive 4/5 times a negative 5/3. It seems that we're going to get a negative product, and also that our 5's kick out here. So we end up with negative 4/3 is our tangent value. And while we're at it, let's go ahead and list our cotangent value as being negative 3/4. So those are the basic identities there, the fundamental or the top 3, and those are why we use them to help us determine the values of other trig functions if one is known. Cheers.